Good morning, everyone. It's a pleasure to be here. I want to begin by thanking Steve and his colleagues for organizing what's a fantastic program. Really looking forward to these 2 days. So, Steve gave me the question to address. Can decision science improve intelligence? Analysis was the original question. And I dropped analysis because I think decision science can do better than just improve intelligence analysis. It can improve pretty much every aspect of intelligence. And Steve Reber, who used to be with ODI and is now an IARPA program manager, advised me 10 years ago at my very first intelligence conference on this very topic, social and behavioral sciences, what they could contribute to intelligence. He said to me, it was before we met face to face, he said, I advise you to start with the bottom line up front. Don't get into all the theory and then conclude with your conclusion. Start with the conclusion. So my conclusion, or the answer to the question in short, is yes. Decision science can contribute to intelligence, and it's not a really complicated answer why. On the one hand, intelligence is fundamentally an exercise in human judgment under conditions of uncertainty, time pressure, accountability to decision makers who themselves are making decisions under conditions of uncertainty, accountability, often with very consequential outcomes that they're reasoning about. And on the other hand, the decision sciences are really nothing other than a shorthand term for the intersection of all areas of science that contribute to understanding how and why people judge and decide as they do. In other words, the descriptive function of decision science, and how they can be aided to do better, which is the prescriptive and normative function of decision science. So on the one hand, what do people actually do when they make judgments and decisions? And on the other hand, how can we help them do better than they currently do? So as with all other areas of science, decision sciences, which I should say it is, decision science is interdisciplinary, so it includes social and behavioral sciences, it includes neuroscience, computer science, cognitive science, as well as probably drawing in from other areas. So for example, you're talking about public administration, and one of the studies that I'm designing now is on job satisfaction in intelligence analysts. So it can draw from a lot of different areas. And as with other sciences, decision science has theories, it has a body of research findings, but I think most importantly, it has a set of methods that can be used to address a very important question in intelligence. Which good ideas work and which good ideas don't work? And I want to put an emphasis on that distinction. Good ideas that work versus good ideas that don't work. Because a lot of times people think about good ideas versus bad ideas. There are good ideas and bad ideas. But all scientists, and I think all innovators within the intelligence community, start off with hypotheses that they think are good ideas. You don't start off with what you think is a bad idea. But just because something is a good idea or strikes you as a good idea doesn't mean it actually works. So the scientific methods inherent in decision science are there to help you ferret out, I think, what are a small set of good ideas that actually work from the much larger set of good ideas that seem plausible. And I think there are two primary routes that decision science can have a positive effect on intelligence. One is through verification. In other words, looking at how good are current practices and products. And the other is through improvement, which is kind of the same process, but instead of looking at the status quo, you're looking at innovations to the status quo or new inventions. For example, structured analytic techniques that have yet to be invented, that maybe IARPA is working on right now. But in both cases, the issue is the same. How do you actually, using an evidence-based approach, figure out what works and what doesn't work? So I'm going to, at this point, focus on 3 areas of research, decision science research, that I've been engaged in recently. And just to give you a couple of examples of how decision science can be applied. So the first study I want to talk about is focused on verification and improvement of strategic intelligence forecasts. And this is a study that I conducted in collaboration with Alan Barnes. Alan was a director of the Middle East and Africa Division in the Privy Council Office of the Government of Canada. And we reviewed 6 years of intelligence products, intelligence memoranda coming out of his division, every single product. We had coded every assessment within every intelligence memorandum to pull out those assessments that were forecasts. And the analysts in his division had to use numeric probabilities. One of those numeric probabilities when they issued a forecast. That didn't go to the consumers, but it was for internal audit purposes only. They had to give a numeric probability. We had the outcomes of those forecasts coded for whether or not they actually occurred, whether the forecasted events occurred or didn't occur, by subject matter experts who showed good inter-rater reliability on the coding of the outcomes. And what I'm showing here in this figure is the frequency of those forecasts as a function on the x-axis of their forecasted probability, and it's broken into 4 quadrants. In the top left-hand quarter, you have the true negatives. Okay, so those are forecasted non-occurrences that actually didn't occur. False positives, in other words, forecasted occurrences that didn't occur. True positives, in other words, forecasted occurrences that did occur. And false negatives, which are forecasted non-occurrences which did occur. So what you'll observe is that the vast majority of the cases fall into the true negative and true positive quadrants, which comprise the accurate cases. And in fact, the accuracy rate was 94%, which was a surprise to no one anticipated that. And this is based on 1,514 strategic intelligence forecasts. We're also able to look at other characteristics of forecasting skill other than kind of the coarse accuracy rate. So this is a calibration curve. Calibration refers to the degree to which the forecaster's probabilities assigned to the events that they're forecasting are proportional to the relative frequency of those events' occurrences in the real world. If they're perfectly proportional, they'll fall on that 45-degree slope. And what you see here is a sigmoidal function, which is indicative not of overconfidence, which you often hear about, warnings about overconfidence, but the flip side of that bias, which is underconfidence. So analysts' forecasts were generally very accurate, but couched in too much uncertainty given the high degree of accuracy. So moving from verification to improvement, the next step was to show that there is a very easy organizational corrective given the scale that they use, which is just to make, you could do this after the forecasts are made, but before they're disseminated to consumers, you make the forecasts more extreme. You move them to the next ordinal position on the scale. And the calibration curve with the red dots shows what happens to calibration after that extremizing transformation. It had a substantial effect on reducing miscalibration. So you could both verify characteristics of forecasting skill, but also do something, once you know what the characteristics are, you could do something to actually improve forecasting skill. The next area that I want to focus on has to do with the communication of uncertainty to intelligence consumers. In this study, Emily Ho, David Badescu, Mandeep Dhami, and I looked at how intelligence analysts interpret the words of estimated probability in these standards, in the lexicons that are used. For example, the National Intelligence Council is available in ICD 203, and the Defense Intelligence Standard is called the uncertainty yardstick. So in the Ministry of Defense, there is a unit that develops analytic methods for defense intelligence, and that's the standard that they promulgate. So you can see there are common terms, but there are different stipulated numeric ranges. So one of the things that we're able to do, again on the verification side of how we could contribute, is we could see how terms like very unlikely and remote chance, which have different ordinal positions in the US lexicon, remote chance is lower than very unlikely, but have identical, there's some synonyms in the British lexicon. How do analysts actually interpret these terms? And what these figures show is analyst assessments of the goodness of fit of the verbal term to the numerical probabilities along the x-axis. You could see that looking at very unlikely and remote chance, that the signatures for the interpretation of those terms are almost perfectly overlapping. So there we're able to say, you know, the Brits perhaps are doing better than the US in terms of that particular element. What we wanted to do was take the data we had collected from analysts and see whether we could improve the communication fidelity by optimizing the numerical ranges that go with those words of estimated probability. So you see the DI standard, the National Intelligence Council, and then the standard 3 at the bottom are standards that we developed based on statistical methods that draw information from the data. And we assess them in terms of their communication fidelity. Communication fidelity or consistency here is simply whether the intelligence analyst's best estimate of the numerical equivalent to that term falls within the stipulated numeric range. And what you'll observe if you look across is that the evidence-based approach outperforms the alternatives, the current methods. It outperforms the US lexicon substantially, as does the British lexicon at the extremes, but it also outperforms the British lexicon more in the mid-range, and overall does pretty well. Okay, so that's 2 out of 3. The last, I have 2 minutes? Okay, that's fine. The last topic I wanted to talk to you about, so the first topic of forecasting accuracy is kind of analytic. The communication of uncertainty to intelligence consumers is kind of post-analytic, and this is kind of at the cusp of pre-analytic to analytic. It has to do with the evaluation step in the processing stage of the intelligence cycle, which is just before analysis. And here, this is a NATO study that is underway under the technical team that I chair on communication and assessment of risk and uncertainty to support decision making. So this is co-authored with Mandeep Dhami, Greg Weaver from Army Research Laboratory, Mark Timms, who's a colleague of mine at the RDC, and Jim Kaidash, who is at the US Air Force Academy, who is now collecting data on another component of the study. So we looked at the NATO standards for encoding source reliability and information credibility, and we wanted to see what the effect of these meta-informational markings are on intelligence analysts' assessments of the accuracy of the information they are receiving, so encoded. We looked at every possible combination. In other words, 6 by 6 gives you 36 combinations. We crossed that with 2 levels of classification, top secret and FOUO, for 72 combinations, and then we took resampled cases to be able to assess the test-retest accuracy of the analysts. So this is the mean probability of 42 analysts' assessments based on the meta-informational tags. And the lines in blue are when the information was coded as top secret. The lines in green are when it's encoded as FOUO. That doesn't look to be a big difference, but it is a statistically significant effect showing that analysts treat information coded as top secret as being more accurate than information coded as FOUO. The first study that I'm aware of that actually shows this with real intelligence analysts. You can also see some interesting characteristics. So the first 3 points in those scales use positive terms, positive polarity terms. The last 2 use negative terms, and you see that huge drop-off in probability where the terms go from positive to negative. The other thing that I want to mention, and I know I'm out of time, but I'm very close to the end, is that as the ordinal position of those 2 scales becomes more incongruent, what happens to the analyst's test-retest reliability is it plummets. So the intra-analyst consistency goes down when the values on the 2 scales are not very closely paired. So here, they're perfectly paired, A1, E5. Here, A5, E1. Perfectly incongruent. And the same thing happens among analysts. So both intra-analyst and inter-analyst consistency plummets when source reliability and information credibility don't agree. Here I'm plotting the standard deviation as a function of the degree of incongruence between those 2 scales. So these are the references from the data that I've just, findings that I've just presented to you. And I hope the examples were informative, and I look forward to more discussion over the next couple of days. Thanks very much.